this video, I'm going to be talking about the other number on the periodic table, the decimal number, which I call the average atomic mass. Some people just call it the atomic mass. Some people, even this periodic table, call it the atomic weight. But technically, scientifically speaking, we're really talking about mass, not weight. That's more of an important distinction in physics. But yeah, I'm going to refer to it as mass, but sometimes you will see some chemists or chemistry teachers or chemistry textbooks or whatever refer to it as weight as well. And so what that number is, it's not the same as mass number, but it is related. It is the weighted average of all naturally occurring isotopes of an element. And it is measured in atomic mass units, or AMU, which is a very small unit of mass. A proton and a neutron are both each roughly 1 AMU. They're both a little bit more than 1 AMU, but very close to 1. Yeah, so like if we take all the isotopes, naturally occurring isotopes of an element, and we consider their masses, and we also factor in how common or how abundant each isotope is, we can calculate the average atomic mass. So this is the formula that we would use. So for each isotope we have, we're going to take the mass of that isotope, and we're going to multiply it by the abundance. Abundance meaning how common it is. So if a particular isotope of, I'm just making this up, I don't know if this is actually true, but just to give you an example, if a particular isotope of iron has a percent abundance of 60%, that means 60% of all naturally occurring iron atoms are that particular isotope with that particular mass. So that's what abundance is. But we're going to use the decimal form. So if it was 60%, we would use 0.6 in this equation. And we would multiply it by whatever the actual mass of that isotope is. And then you would do the same for the next isotope if there is a second isotope. And then you would repeat this process for each isotope that an element has, and then you would add the products of each of those together. Okay. Another way of thinking about this number is when you do this calculation, what it comes out to be is it's just simply the average mass of an atom of that element. Okay. So just looking here, zinc has an average atomic mass of 65.38 AMU. That means on average, a zinc atom has a mass of 65.38 AMU. Now, probably no individual zinc atom has that exact mass, okay, because that's not really that close to a whole number. And typically, the individual isotopes will have atomic masses that are close to whole numbers for the individual isotopes. But the average is 65.38, so some zinc atoms will be lighter than that, some will be heavier than that, but that's the average mass of all zinc atoms. So here's an example for magnesium. Magnesium has 3 naturally occurring isotopes, magnesium-24, magnesium-25, magnesium-26. Those are the mass numbers. Now, I've written the actual atomic masses of each isotope, okay? And even these I've rounded off a little bit, but it's approximately these. And notice they're very close to the mass number, but not exactly the same. There's 2 reasons for that. One is that, remember, mass number is protons plus neutrons. And I said that a proton and a neutron are each around 1 AMU, but not exactly. They're actually each a little bit more than 1 AMU. So with that, we would actually expect this to be larger than the mass number. Okay, so that explains why these differ by a little bit, but that doesn't really explain why this is smaller. So the other thing that happens is that when a nucleus forms, a little bit of mass is lost. So the total mass of the nucleus is actually a little bit less than the mass of if we had summed up the protons and neutrons before they combined. We call this mass defect. Now this is a little bit more complicated. You don't really need to know too much about that. For now, you may learn about it later in your chemistry class, but probably not till closer to the end of the year. But just, that's why they differ a little bit. That's really all you need to keep in mind, is that these might not be exactly the same. And you really don't even need to know exactly why, but if you're curious, that's why. The atomic mass will be a little different than the mass number. Sometimes they won't even give you these, and if they don't give you these, then you can just use the mass numbers in your calculation, because these are approximately the values. But when they give you these more exact values, we'll go ahead and use those. So what we're going to do is we're going to take each isotope and multiply the mass of that isotope by its abundance. So for magnesium, starting with the first one, we've got 23.985 AMU times its abundance. Now these are given as percentages, so I'm going to convert that to a decimal. So just divide by 100 or move the decimal 2 places to the left. So that's 0.7899. And then I've got the second isotope, 24.986 AMU times, this would be 0.1. And I'm going to keep all these zeros at the end for sig fig purposes. If you remember, those zeros are all significant because they're at the end of the number. They're trailing zeros, and there's a decimal point in the number. So I should keep those for sig fig purposes. And then this one has 3 isotopes, so I have to do this for all 3. Okay, and let me get my calculator. Okay, and so we get, and I'm going to use sig figs here. So this first one, multiplication, 5 sig figs, 4 sig figs. So I'm going to round it to 4 sig figs. So that's 18.95. Okay, and then that's going to be AMU. This is AMU. This has no unit. So when you multiply by something that's unitless, the unit doesn't change. And then, well, that's just 0.1, so I'm just going to move the decimal 2 places. So that's 0.2499 AMU if I round that to 4 sig figs. And then this last one, 4 sig figs, sorry, I did this one wrong. I moved it too far. This should be, the second one should be 2.499. And then the third one should be 2.861. And then I add those all up. And then I'm going to round to sort of the leftmost decimal place. So these go to the 3rd decimal place or the thousandths place. This only goes to the 2nd or the hundredths place. So that's the rule when we add. So I'm going to round this to the hundredths place. So it rounds to 24.31 AMU. So that, according to the numbers that I started with, would be my average atomic mass of magnesium. If I look at the periodic table here, it says, this one says 24.304. So not exactly the same, but pretty close. 24.304, 24.31. So when you do the calculation and you compare it to your periodic table, you might not get exactly the same number because it's based on the numbers that you're starting with, which in theory should be, universal, but depending on the database that they're obtained from, may differ slightly. So your answer should not be wildly different. If it is wildly different, then you probably did something wrong, but it might be, ever so slightly different due to just rounding or, based on the numbers that you started with being slightly different than a different source.